to start. So you got this reaction going on, right? So which statement best explains why the reaction should be classified as a Bronsted-Lowry acid-base reaction, right? I mean, basically an acid-base reaction. Why is it an acid-base reaction?
Number one.
The ammonium ions, the ammonium ions they got H+1, now they don't have H+1. So that means number one is fine. Is number two, so basically it's number one, only number one, right? Because that's what the theory is, that something is a proton, no, that's an acid, right? Now remember, in the Bronsted-Lowry acid-base reaction, it's not necessary that a salt gets produced. The definition is pretty broad. Someone losing H+1, someone gaining H+1, that's it. It's got nothing to do with salts. And ammonia is not always basic because ammonia is basic, but ammonia can also lose H+1 ions. It's got H+1 ions, so it can possibly lose H+1 ions. So we're not really sure whether it's always basic, so that we can't be 100% sure about that. Okay. Chalo, ignore this one. The table gives the concentration and pH of the aqueous solutions of two compounds X and Y. Either compound could be an acid or a base. So there's 2 mole per dm cube X, 2 mole per dm cube Y. This has a pH of 6, this has a pH of 9. Student P concluded that X is a strong acid. And is he right? Is student P right?
No.
Okay, it is an acid though, right? But it's not a strong acid. And student Q concluded that the extent of dissociation is lower in X than in Y. Look at the pH, who's going to dissociate more? Who's stronger?
X.
Why do you think X is stronger?
Because it has a lower pH.
Well, X is an acid, right? Y is actually a base, right? So when you're 7, right? I mean, 7 is the midpoint. 7 is when it's neither, right? So he's not talking about whether it's acid or base. He's just talking about which one is stronger, which one is more, it's going to dissociate, which one is going to dissociate more. So relatively speaking, the base over here is relatively a stronger base, right? Is that clear?
Oh, because it's 2 more than 7.
Yeah. I mean,
Okay.
6 is a lot closer to 7. 9 is like a little further off, TK. So the extent of dissociation is lower in X. That's fine. That's fine, TK. So Q is right? So only Q is right. As the next one is which statement about the theory of acid bases is correct? Water can act as an acid or a base. Is that correct?
No. Yes.
TK, here's water. Water could lose an H+1, right? So that
okay, yeah.
plus water's got lone pairs and it can gain an H+1 as well. In that case, it's going to become H3O +1. So it can actually do both. Remember, water is amphoteric. It can actually do both. I said that's why bases and acids, they both dissociate in water, because if you add an acid to water, the acid ionizes because the water is acting as a base. If you add a base to water, the same thing happens. The base accepts H+1, so the water is the one that ends up losing H+1 ions. I say anyway, sulfuric acid does not behave as an acid when dissolved in ethanol. Sulfuric acid, when does it dissociate? In what medium would it dissociate?
Water.
Because so normally it's going to dissociate in water, right? It's not going to dissociate in ethanol. Normally, it's just water that they dissociate in, because water is highly polar. So 2 is correct. Does not, yeah. The ammonium ion acts as a base when dissolved in liquid ammonia. mean, you got the ammonium ion, right? Ammonium ion was this thing. It's NH3. Plus the N has lone pair, so the H+1 gets attracted to it, right? So that's an ammonium ion. Can it act as a base?
No.
Because it can't gain more H+1 ions, so that's wrong. So one and two both are correct. That's the next one. You got two reactions going on. The hydroxide ions are neutralized by the acid. You see? He's saying which of the following statement helps to explain why tooth enamel is this thing. He's saying why does tooth enamel dissolves more readily when saliva is acidic? So why does it dissolve in acidic conditions?
Is it number 2?
What about the first one? If the conditions are acidic, the hydroxide ions are neutralized, right?
Yeah.
So the OH ions they decrease. तो क्या होगा? Where would the equilibrium shift?
Towards the right.
So it's going to dissolve, right? So when the conditions are acidic, that's one of the reasons why it's going to dissolve, right? Then 2 is not right because I said, 2 is right, right? I mean, at least it's a factual statement that if the conditions are more acidic, where would the equilibrium shift? Backwards, right?
Yep.
So how does that help tooth enamel dissolve? I mean, how does it help it in dissolving? Any idea?
So for the second reaction, it would shift backwards.
Yeah. So how does the second reaction affect the first reaction? Like how does it help in how does it make tooth enamel dissolve?
Because there'll be less of the phosphate ion. It will decrease.
It's going to decrease, it's going to move forward, right? So that's why. Calcium ions react with acids. They don't. Calcium ions will not react with acids because we've never studied any reaction where calcium ions. Firstly, they're both positive ions, so they don't have anything to do with each other. So calcium ions are not going to react with acids. Okay. As the next one, he's saying that sulfuric acid behaves as a strong acid. So sulfuric acid is a strong acid, while this ion over here behaves as a weak acid. So which statement about 1 mole per dm cube sulfuric acid is true?
So the statement strong acid, does that mean it donates more H plus ions?
Yes.
Is that what it means? Okay.
So this is a strong acid. It forms this ion, and he's saying this ion is a weak acid. So is the first statement correct? Number 1.
No.
Why? Why is the first statement? I mean, he said it's a strong acid, right? I mean, he did say that.
So it is true.
So it's going to produce more H plus ions. So the concentration of H plus ions is going to be high, right? Is the concentration of sulfate ions going to be high?
No.
So the concentration of HSO4 ions are going to be high. I mean, both of these concentrations would be high, but the HSO4 does not dissociate, so there's not going to be a lot of sulfate ions. So that's wrong. Is the concentration of HSO4 and sulfate ions, so this concentration would be high, and the concentration of sulfate ions is going to be low because HSO4 does not dissociate, right? So that means they're not going to be equal. I mean, the HSO4 ions would be present in a large amount, and since it's not dissociating, so the sulfate ions would be present in a very small amount. So the third statement is also wrong. TK, clear?
Okay.
So where I'm just going to add a point since we were doing acids. I'm going to talk about monoprotic, diprotic, triprotic acids. So you got monoprotic, diprotic, I mean, usually it's so the question is what are these acids, TK? So the thing is that when you have a monoprotic acid, it just donates one H plus one ions, right? So you got HCl, it's going to produce H plus one, and it's going to produce Cl minus one, right? So just one donates one H plus one ion, right? A diprotic acid would donate two. So it's going to donate two H plus one ions. Similarly, you got triprotic acids. So now triprotic acid would donate three H plus one ions, right? So is that clear? What's a diprotic, monoprotic, triprotic acid? Was that clear?
Yep, it's clear. Yep.
So now the point I'm trying to make about at least diprotic and triprotic acid is, don't think of them as one acid. Or don't think of them as a single dissociation. So for example, if you've got sulfuric acid, sulfuric acid is something that looks like this. It's I think it's, and it's got an OH and it's got another OH, right? So sulfuric acid will not lose the two H plus one ions together. I mean, it's got two H plus one ions, right? It's not going to do them in a single step. It's not going to happen in just one go. What will happen is that sulfuric acid would first, so it's going to first lose one H plus one ion. So you'll be left with HSO4 minus one. And then that HSO4 minus one, that would lose another one and it will become SO4 minus 2 TK. So you clear like dissociations, they don't happen in one go for diprotic, triprotic acids. They're the multiple steps involved, right? Is that clear?
Yep, it's clear.
So So the thing is, the idea is that there's going to be a first dissociation, then there's going to be a second dissociation. So think about them as two different acids or two different dissociations. Now, which one do you think is going to behave as a stronger acid? Is it going to be sulfuric acid or the hydrogen sulfate ion? Remember, it's two completely different acids. Sulfuric acid dissociates, forms this ion. This ion is a separate ion, and then this dissociates. So it's like completely two different acids, right? So now, which one out of the two do you think is going to be the stronger acid, and why?
Is it the second one?
So that's going to be the stronger or the weaker one,
No, I think the first one's the stronger one
and why?
because it dissociates into it dissociates more than the
Nee, but
second one
but why would it dissociate more than the second one?
because um it's the first one. Is there also a third equation as well?
Nee, after that, there's no further dissociation because you've run out of H plus one ions, right? You had to
Oh
let go
yeah.
of the first one. So the point is dissociation becomes more difficult, right? And the reason for that is it always becomes more difficult. Like if you've got phosphoric acid, the first one is the easy to lose, and then the subsequent H plus one ions, it just becomes harder to lose, right? And the reason is that after the first one is a neutral molecule, the second one is a negative ion, right? What do you think negative ions do? They attract H plus one. So it's harder for a negative ion to lose H plus one ions. Is that clear?
Yep, it's clear.
So negative charge on the ion increases. And that vice versa leads to more attraction for H plus one. So it becomes harder to lose H plus one ions. So the first one is going to be the stronger one. And the second one is going to be the weaker one. Okay. And the same pretty much applies to phosphoric acid. The dissociation, they become weaker and weaker acid, right? So if you look at phosphoric acid, so phosphoric acid is going to lose an H plus one, then it's going to become H2PO4 minus one, sorry. And then next step, the H2PO4 minus one would lose an H plus one ion, and it would become HPO4 minus two. And then you got HPO4 minus two. And it would eventually become PO4 minus three. So again, same reason, it's going to become harder to dissociate. So dissociation becomes more difficult. Okay, and it's the same reason. Okay, so so keep this in mind. Don't think of phosphoric acid as a single acid. Think about it as two completely different acids, or three completely different acids in this case. Okay, is this thing clear?
Yep, it's clear.
So we'll just move on. Okay, so we're doing acids and bases. We'll just move on, and we will start talking about water dissociation constant ionic product of water. Now that's related to acid and bases. It's also known as the water constant, which is Kw. So that's Kw. Now the thing with this is that water ionizes. Do you remember? So why is water important? I discussed this earlier. That why is water important? वो पहले एक drawing बनाई थी कि I explained to you that. I mean, this is the basic idea, right? I mean, let's just copy the same thing. Okay. So I explained to you that everything is happening in water. So the entire concept of acid and bases is basically related to water, right? It's basically trying to figure out whether in a solution you got more H plus 1 ions, you got more OH ions. Okay, that's the basic idea. You want to figure out who's greater, right? So that's the whole idea. That's that. Now the thing is, this equation over here is not really I mean, this is used as a simplified version. This is not exactly what the equation is. The real equation looks something like this. That it's basically two water molecules reacting with each other. And what happens is that one of the water molecules loses an H plus 1, so it becomes OH minus 1. And that H plus 1 goes to the other water molecule and it becomes H3O plus 1. Now remember this fact that H plus 1 ions don't roam around independently in water. As soon as an H plus 1 is formed, some lone pair from water would get attracted to that H plus 1. And it would eventually form H3O plus 1. Okay? Is this thing clear?
Yep, it's clear.
But these equations are kind of interchangeably. I mean, we used to, so just remember that whenever you hear the term H plus 1 ions, or you hear the term H3O plus 1 ions, they're basically the same thing. Okay, so this is kind of the same thing, okay? And both equations, you can interchangeably use them. Most of the time, you're actually using the first one, this one. This is what you've mostly seen. This one not used that often, okay? But remember, it might appear. So just remember, H3O plus 1 is the same as H plus 1. You don't have H plus 1 roaming around in water, so it's basically H plus 1 sticking to water molecules. अच्छा अब ये कि the next part is what do we do with this, right? Now the idea is that when you have a solution, right, water would ionize and water would ionize very little. The concentration of water would be, बल्कि नीचे लिख लेता हूँ. अच्छा, so you've got water ionizing, right? It's forming H plus 1 and it's forming OH ions. Now, the concentration of water is going to be very less. When the amount of water that ionizes, it's very, very less. It's 1 times 10 to the power minus 7, and it's going to produce 1 times 10 to the power minus 7 mole per dm cube. And this happens under standard conditions. Okay, so this is under standard conditions, which is 298 kelvins, room temperature, and it's 1 atmosphere pressure, and forget the concentration, right? So there's very little water that's ionizing. You get very, very tiny amount. Is that clear?
Yep, it's clear.
So since it's an equilibrium reaction, right? I mean, this entire reaction, this entire reaction is an equilibrium reaction. So what we can do is we can apply Kc. What is Kc? Kc is product concentration, which is H plus 1 into OH ions, and divide by the water concentration, which is so product over reactants, right? You get this Kc expression. Now the thing is that in an equilibrium reaction, if water is in large excess, if everything is water, then water concentration is taken as a constant. Is that clear?
Yep, it's clear.
So whenever you take something as a constant, you take it as 1, right? So basically you can either remove it. I mean, like if you have solids, you just remove it from the expression. Or the other way to write it is you can put the constants together. So it's basically Kc dot water concentration. You call this Kw, which is basically H plus 1 concentration times OH ion concentration. So there's kind of nothing new in this, except that you just removed water from the expression because it's going to be a constant. Is that clear?
Yep, it's clear.
And I told you that what value would Kw have? Kw would be equal to 1 times 10 power minus 7. That's the concentration under room conditions, multiplied by 1 times 10 power minus 7. That's the concentration of OH ions under room conditions. So your value of Kw is going to be 1 times 10 to the power minus 14. And that's going to be mole squared dm minus 6. I mean, it's concentration times concentration, right? So that's going to be your answer for the value of Kw. Now, water has an equilibrium constant, and that's Kw. Or water's dissociation is Kw, right? Which is basically Kc. And Kw is a constant, except that it only changes with temperature. I said it only changes with temperature. And it actually increases with temperature, because water ionizes a lot more if you have a higher temperature. Okay, is this clear?
Yep.
Now, but otherwise it's a constant. So we're basically dealing with things at room temperature. So we're only talking about the constant. So the idea is that this Kw remains a constant. It's always going to be 1 times 10 power minus 14. So what's going to happen is that if the solution becomes more acidic, so if your H plus 1 concentration becomes higher, vice versa, what happens is that your OH ion concentration decreases. But your answer I mean, your product would still be 1 times 10 power minus 14. Is that clear?
Yep, it's clear.
So in an acidic environment, H+1 goes up in the solution, OH ends come down. Vice versa, in a basic environment, what's going to happen is that the H+1 decreases and your OH end goes up. But the product still remains 1 times 10 to the power minus 14. And we already did the basic condition, right? I mean, this is basically basic. So the idea is that your KW does not change. No matter what type of water do you have. You've got blood, you've got stomach acid, you've got water anywhere. The KW remains exactly the same. The H+1 goes up, the OHN goes down, but the product remains exactly the same. The H+1 go down, the OHN goes up, product still remains exactly the same. And also remember the two of them are not going to go up together. It's either going to be acidic, so either the H+1 goes up and the OHN goes, the quantity of OHN decreases, or vice versa. Okay, so one goes up, the other one goes down. Okay, is this clear?
Yep, it's clear.
Let's see. So just remember this idea that water KW would always be a constant. Okay. So ठीक है, so आगे ना we'll discuss pH. Where does pH come in, right? pH is linked with, because you're dealing with water. So we'll be talking about how does this fact, I mean, how does this expression link with pH, ठीक है? तो वो फिर next class, ठीक है? We'll do that in the next class, ठीक है?
Okay, so is that going to be tomorrow?
ठीक है, let's have a class tomorrow then, ठीक है?
Okay.
Okay, take care, beta.
Thank you, Allah Hafiz.
Allah Hafiz.